Okay, we will now look at the next two important applications of Bayes' theorem. So these are the open mapping theorem and the closed graph theorem. Okay, so before we start, let us recall some notation. So if you have a vector space and you have two sets A and B, then A plus B is nothing but the algebraic sum. So the set of all x plus y, x is in A, y is in B. Similarly, if lambda is any scalar, then lambda A will be set of all lambda x, x is in A. So if you take 2A, this is a set of all elements of the form 2x. So that is x plus x, and so it is contained in A plus A. So 2A is always contained in A plus A. This is always true. But the converse need not be true. For instance, if I take A to be the set in the real line, say minus 2, minus 1, union, say 1, 2. Then 0 will be in A plus A, but it is not in 2A. Okay, so because 0 is not in A, so it is not in 2A also. But if A is convex, and if you have x and y in A, then you can write x plus y is twice x plus y by 2, and A being convex, x plus y by 2 belongs to A, so this belongs to 2A. Therefore, if A is convex, this implies that 2A is the same as A plus A. Okay, so this is some notation which we will need in the proof of the open mapping theorem, which you are going to do now. So we will first prove a proposition. So VW Banach T belong to LVW, so that's a bounded linear operator or continuous linear operator which is onto. This is the main hypothesis which we want to remember. Okay, then there exists a C positive such that the ball in W, center 0, radius C, is contained in the image of the ball in B, center 0, radius 1. So what does this say? This says that if you take a neighborhood of the origin and T is an onto continuous linear map, then the image is also a neighborhood of the origin. So this is what, from this we will be able to show that T maps open sets into open sets, and that is called the open mapping theorem. Okay, so let us prove this. We will do it in two steps. So the first step will be claim there exists a C positive such that BW 0 2C, that is the radius 2C center origin in W, is contained in T BV 01, image of the unit ball in V, closure. Okay, so it's a slightly bigger set, and in a slightly bigger set we say we can accommodate a ball. Okay, so let us set, so we want to establish this claim. So let us set x equals xn equals n times T BV01 closure. Then each xn is closed. Also, T is onto, so this is where we use the ontoness of the map. So every element in W is a image of something in V, and you can scale it, and therefore you can show that in fact W equals union n equals 1 to infinity xn. So every y will have to be any x will be n times bv01, and therefore y will be in n times tbv01 closure. Okay, so this is entirely because of the ontoness of this map. So what does the Bayes theorem say? So Bayes implies not all xn can be nowhere dense because W is complete. This is where we are using the completeness of the range space. Okay, so W is complete, so it cannot be the countable union of closed nowhere dense sets, and therefore at least one of the xn's is not. So there exists an n such that xn interior is not empty. But what is xn? It is just a scaling of x1, namely tbv01 closure. Therefore, if that has non-empty interior, then any scaling of it will also have non-empty interior. So this implies tbv01 closure interior itself is non-empty. Okay. So what do we know? So this interior is non-empty, so it contains a ball, a point and a ball around it. Okay, so there exists y naught in W and a C positive such that BW y naught 4C, I will take some radius, I am going to take it as 4C with some foresight, and that will be contained in TBV01 closure. So in particular, y naught itself belongs to TBV01 closure, and if you take any z such that and if you take any z belonging to B0 4C, you have that y naught plus z belongs to TBV01 closure, because y naught plus z is precisely an element in TBW. So this is W here. Okay, y naught 4C. Okay, now BV01 is a symmetric set and T is linear. Therefore, if y naught belongs to it, this also means that minus y naught belongs to TBV01 closure. So now I am going to write Z as y naught plus z plus minus y naught. So this belongs to TBV01 closure plus TBV01 closure. But this set is convex because BV01 is convex, T is linear, so the image is convex, the closure is convex, and therefore by our earlier observation this is 2 times TBV01 closure. So the ball center origin, so this shows that BW04C is contained in 2 times TBV01 closure, and therefore if you scale it by 2, so then you get whatever the claim which we wanted, namely BW02C is contained in TBV01 closure. So this condition is immediately proved. Okay, so that is the first step where we have used the two hypotheses, namely T is onto and the fact that W is complete. So step 2. So now we are going to use the fact that V is complete. Okay, so we must show, so to show, now we are going to show that BW0C is in fact contained in TBV01. Okay, so the closure, by halving the radius, we are able to remove the closure. So that is what we want to do. Okay, so let y belong to, so let y belong to BW 0C. So to show there exists x in V, norm x V less than 1, such that Tx equals 1. That's what we need to show now. Okay. So let epsilon be some positive number, arbitrary. Then, so y is in BW0C. So 2y belongs to BW 0 2C. Therefore, it belongs to, which is contained as we know in TBV 01 closure. So that means given any epsilon, 2y can be approximated as closely as you like by an element in TBV 01. Okay. So there exists a z such that norm z is less than 1, and then 2y minus tz is less than epsilon. So from this we say there exists a z1 such that norm z1 is less than half, so that twice that will be in 1, and then norm 2y minus 2tz1 norm is less than any epsilon. I am going to take epsilon equal to c, so that this implies that y minus tz1 is less than c by 2. Okay. So y minus tz1 is less than c by 2. So 4 times y minus tz1 belongs to BW0 2C. So it can be approximated by image of something which is in BV01 as closely as you like. So from this you have that there exists Z2 in V, and norm Z2 I take as less than 1 by 4, so that 4 times that will be what we want, and such that norm of y minus tz1 minus tz2 is less than c by 4. So we now take 8 times this vector, and you can do the same game, and therefore eventually by induction there exists a Zn in V such that norm Zn is less than 1 by 2 power n, and norm of y minus t z1 plus Zn is less than c by 2 power n. Okay, fine. So look at the sequence z1 plus Zn. What is the difference of two consecutive terms? The difference of two consecutive terms is Zn plus 1. Its norm is less than 1 by 2 power n plus 1. Sigma 1 by 2 power n is a convergent series, and therefore this is Cauchy. So this is a fact which we have already used before. If you have a sequence whose general term xn is less than norm xn is less than norm xn plus 1 minus norm xn, the difference between two consecutive terms is less than an, sigma an is convergent, then xn is a Cauchy sequence. So this is the fact which we are using. So V complete, so now we are going, the last part of the hypothesis implies z1 plus zn converges to some x. And then you have from this condition here that y equals tx. And what is norm of z1, norm of x? It is less than or equal to sum of the norms of all this thing. That's a convergent geometric series, and therefore that will be strictly less than 1, since each norm zn is less than 1 by 2 power n. So there exists a y, and so we have proved that there exists an x with norm x less than 1, and this is exactly what we wanted to show, such that Tx equal to y. Okay, so that proves the proposition completely. So now we will make a remark. Because everything is going to be scaled, so if R is positive, then there exists an S positive such that BW0S is contained in TBB0R. Okay, so this is obvious. Okay, so we did it for one, then it's just a question of scaling it. And so now we can prove the theorem. Open mapping theorem. So VW complete, T from V to W onto continuous, then T is an open map. That means it maps open sets into open sets. Okay, so proof. So let G open in B. So to show TG open in W. So this is non-empty, of course, otherwise there's nothing to do. Okay, so TG is open. So let us assume that Y belongs to TG. So this means that there exists an X because T is on 2, such that Tx equals Y and X in G. So X is open, not X, G is open implies X plus B0R is contained in G. This is BB. Okay, so therefore Tx, that is Y, plus T of BB0R is contained in Tg. But there exists a BW0S which is contained in T of BB0R, that is what we remarked, and therefore this implies that Y plus BW0S is contained in TG, and this implies that TG is open. And this proves the open mapping theorem. So there are several applications of this theorem, and some of them are really very interesting. So okay, corollary. T V to W VW Banach, T a continuous bijection implies T is an isomorphism. So V and W are Banach, T is continuous and it is a bijection, so it is on 2. So this implies that T is an open map. And this implies that T inverse is continuous. Therefore, it's an isomorphism. So that's just that. So now this leads to another very interesting corollary. V, a vector space, complete with respect to two norms, norm 1 and norm 2. Assume there exists a C positive such that norm x1 is less than or equal to C times norm x2 for all x in V, then the norms are equivalent. Proof. So you take the identity map from V with norm 2 to V with norm 1. So this is an on-to map, and further it is also continuous because of the given condition. This condition tells you that norm x2, norm x1 is less than or equal to C times norm x2, so this is continuous. And it is also a one-to-one map, being the identity implies this an isomorphism. So identity is an isomorphism, therefore the norms are equivalent. So let us see an example of an application of this very nice result. So let us take C01. Then you have two norms there. One is the usual sup norm, which is norm infinity. The other is norm f1, which is integral 0 to 1 mod ft dt. In an earlier set of exercises, we showed that with this norm it is not complete by exhibiting a Cauchy sequence which cannot converge inside the space. Now let us do it through the open mapping theorem. Okay, so you have that norm f1 is less than or equal to norm f infinity, and we know that, we also saw that norm 1 and norm infinity are not equivalent. We produce a sequence, namely f of t equals t power n, and therefore the norm 1 is 1 by n plus 1, which goes to 0, whereas L infinity norm is just norm 1, and therefore they cannot, you can't have a inclusion of this type. Okay, inequality of that type. So we know that these are not equivalent, and therefore this implies that C01 with norm 1 is not complete. We already know that C01 with norm infinity is complete. If this were also complete, you have two norms and one of them less than or equal to the other, and the previous corollary said they should be equivalent, but we know they are not equivalent, therefore this is a proof that this is not complete. Okay, so now we are ready to move to the next theorem, namely the closed graph theorem. So let us first define the graph. So V to W, so T from V to W is a mapping. So we define G of T is set of all x Tx x in V. So this is called the graph of T. So this is subspace, it's a linear subspace of V cross W. Okay, so if T is linear and continuous, okay, then implies GT is closed. Why? So let xn, Txn converge to xy in V cross W. So that means xn goes to x, Txn goes to y. But T is continuous, so Txn has to go to Tx, so y has to be equal to Tx, and therefore xy is xTx, which is in the graph, so this implies that GT is closed. The beautiful thing is the converse is also true. Okay, so this is the theorem. So this is the closed graph theorem. So VW Banach, T from V to W linear, GT closed implies T is continuous. So we have seen many ways in which you can prove the continuity of an operator. Continuity Txn, xn goes to x implies Txn goes to Tx, xn goes to 0 implies Txn goes to 0, or the image of the open unit ball is bounded, or closed unit ball if you like, and then norm Tx is less than or equal to C times norm x. So these are various criteria which we use so far, and this is now a new one. It says if you have a linear map and Banach spaces, that is important, then if the graph is closed, then T has to be continuous. So this is one more nice result. Okay, so let us prove this theorem. So proof. So you have let us define norm x1 equals norm xv plus norm tx in W. Okay, this is trivially a norm that you can check without any problem. Okay, so I will leave that checking for you. So let us take xn Cauchy. So this is norm on V. Xn Cauchy with respect to norm 1. But norm 1 is a sum of these two things, so this implies xn Cauchy with respect to norm x, norm V, and Txn Cauchy in W. Therefore, we have both spaces are complete, and therefore you have xn goes to some x in V and Txn goes to some y in W. Now you know that GT is closed, implies y equals Tx. So we get xn goes to x in V, Txn goes to Tx in W, and therefore you have that norm V with norm 1 is complete. So V with norm 1 is complete, V with norm V is also complete, that is we already know because it is a Banach space, and you have two norms on it, and you also know that norm xv is less than or equal to norm x1. Therefore, norms are equivalent. Therefore, norm xv is less norm x1 sorry is less than or equal to C times norm xv. What is norm x1? It is a sum of two norms, so in particular one of them, namely norm txw, is less than or equal to C times norm xv, that is T is continuous, and therefore we are through. Okay, so we this completes the proof. So this is one more way of showing that the mapping is continuous. Okay, so how is this used? So use of CGT, closed graph theorem, to prove continuity. So VW Banach and T from V to W linear. So to show GT is closed, this is what we have to do. So what you have to do, you let xn go to x in V, Txn goes to y in W, and then prove that y equals Tx. This will show then the graph is closed and therefore T is continuous. Okay. Now this is the beauty of this theorem. So normally when xn goes to x, and if you knew Txn converges, then you can easily show Txn goes to y. Now which we can't do in general, but to show that if you have Banach spaces, if xn goes to x and you assume that Txn goes to y, so you are permitted to assume the convergence of Txn, then somehow you show that y has to be Tx. So that is the only part which you have to do, and therefore it's a very efficient method of showing the continuity of this. Okay, so we have now proved all the three grand theorems which follow from Bayes' theorem, and we will see many applications in the lectures to follow. Okay.